Okay, let's do another example. Example 3. And this is gonna be energy balance. And temperature profile for a sphere. Now we're going to talk about sphere geometry. We're going to have heat generation, and one-dimensional heat transfer. In the radial direction, R direction. Okay, so we say, so let me show you the geometry. Basically, I have this sphere, which has a radius R, and there's heat generation, uniform heat generation. Let's say uniform, so that the fancy R dot is constant. And still, you can actually make a shell balance here. And you can talk about the QR coming in, QR coming out. And we can write down heat in minus heat out plus generation is equal to accumulation. And the accumulation is going to be 0 if we assume the steady state. If we assume that the temperature profile does not change with time, nor the fluxes. And heat in is basically, this time my shell is a spherical shell, meaning that it's like a closed surface, unlike the cylindrical shell. The cylindrical shell was open on both ends, but this time my spherical shell does just look like sphere. So it's a closed surface with a thickness delta R. And the heat in is basically the QR, the flux times the surface area of the shell, which is the surface area for a sphere is 4 pi lowercase r squared. And it's evaluated at R, and whatever is coming out is QR times 4 pi r squared again, but it's calculated at R plus delta R this time. Plus the generation term is basically the fancy R dot, volumetric, times the volume, the differential volume, the infinitesimal volume of the spherical shell, which is basically the surface area 4 pi r squared of the shell times the thickness of the shell, which is delta R. That's equal to 0, the accumulation. Now divide by 4 pi delta R and take the limit as delta R goes to 0, and you would find the following: minus d over dr QR r squared plus fancy R dot times R squared is equal to 0. Then from here, the QR r squared, d QR r squared is equal to fancy R dot R squared dr, and you take the integral from, for example, 0 to any R, and this is from R QR is from 0, because r is 0, the RQR becomes 0 at the boundary, to any RQR. Okay, and you would find out that RQR minus 0 is equal to the integral r squared dr is r cubed over 3, so fancy r dot over 3 r cubed minus 0, because the r is 0. So you found out that QR comes out to be fancy r dot over 3 r squared, because one of the r's cancel. So that's the heat flux
It should be QR square on the LHS, right?
Oh yeah. I'm sorry. That's exactly, that's a misprint. That's r squared QR. So you get basically r dot fancy r dot r over 3. Thank you so much for the correction. Who is correcting?
Nihil Shreyas.
Nihil, thank you so much. Any other questions or corrections? Okay.
Why is there no plus C?
Oh, because this is a definite integral. You can also, that's a great question. You can also follow the other route where you have this without actually putting limits here, right? You can say QR r squared is equal to r dot r squared dr, and you find out that QR r squared is equal to fancy r dot r cubed over 3 plus c, because that would be an indefinite integral. Then you can actually write down a boundary condition. You can say at r is equal to 0, QR times r is equal to 0, because this r is equal to 0, right? And then you would find out that c is equal to 0, right? You would find the same answer. Does that make sense?
Yes, thank you.
Okay, great. No problem. Okay, so we have about 19 minutes. So that would be the flux as a function of radius, right? Okay, good. How about the temperature profile? We need the Fourier's law. We need, as always, to write, as always so far, I would say, we need to write Fourier's law to get T profile from the Q. Okay, so the QR is nothing but minus K dt over d r this time. The heat is transferred towards the r direction. And we are actually using some assumptions here. We are assuming that the temperature is not changing with the theta, the radial, the angular position. It's just changing with the radius. It's isotropic, so it doesn't matter whether you change from one angle to another, but it matters if you change the radius. So it's a one-dimensional problem still, and you can write the QR as minus k del dt over dr, and there are no angular terms. Like there is no term such as dt over d phi or dt over d theta. And we equate it to this equation, and we write down fancy r dot r over 3, and from here we find the dt is equal to minus fancy r dot over 3k r dr, and then you take the integral of both sides. You can say you can either write down the equation and find the constant using the boundary conditions, or you can actually write down the boundaries at this point. For example, you can say it R is equal to capital R, T is equal to TR. But let's use the other approach. Let's write down, let's calculate the integral using indefinite integrals and then use the boundary condition. And this is T is equal to, let's write it here. Temperature comes out to be equal to minus fancy R dot over 3K. The integral of RdR is R square over 2. R square over 2 plus C, some constant, and use boundary condition to find C or relate C to any known temperature. So we can say boundary condition at R is equal to capital R is at the surface of the sphere. Let's call the temperature as TR. Okay. And if you plug in, you would find TR is equal to minus fancy R dot over 3K R squared over 2 plus C. So you find the C as TR plus fancy R dot R squared over 6K. Yeah, that's it. And you plug the C in here, and you would get T is equal to minus fancy R dot R squared over 6K plus TR plus fancy R dot R squared over 6K. Or if you rearrange, you can write it as TR plus fancy R dot over 6K R squared minus R squared. That's the temperature profile of the sphere, right? You can actually attempt to get like more condensed form of this equation. You can actually divide by R squared, and you can make it look like, if you like, TR plus fancy R over 6K. Divide this term in parentheses to R squared, and you would get 1 minus R over R squared. Yeah, you can also write it down as this. Both is equally well. And you should check the units to see whether it makes sense. Check units. Kelvin is on the left-hand side. It's Kelvin plus the R dot is watt per meter cube. R square is meter square. Divided by K has the units of watt per meter Kelvin, right? And this is unitless. 1 minus R over R square is unitless. So you basically get Kelvin here. So you can see watts cancel, meter cancels with these, and you get Kelvin here. Makes sense. Kelvin is identical with kelvins. What else can we do? Is there any other is there any other check that you can think of? The limiting case, you can basically say limiting case for fancy R is equal to 0, which is no heat generation. You can actually get an idea about another type of system where you don't have any generation. T comes out to be TR plus T comes out to be TR. What does it mean? Okay, anybody who can tell me about what this means? temperature would be
Temperature is uniform, constant.
Exactly, temperature would be uniform. Imagine that this is the R, this is your temperature direction, and this is your, say, this is your temperature, this is your radius, imagine. It's basically the same overall TR. It would not change because the reason is because if it's at steady state, it's going to lose all its energy until it's in equilibrium with the air, right? It's going to just equilibrate with the air, and since there is no heat generation, it's just going to stay as cold as air or as hot as air. But if you have heat generation, it should lose whatever it has to the surrounding environment, right? And you can calculate also how much heat it's actually losing, right? You can say how much heat is it losing. So you can say it's just the heat flux QR times the 4 pi r square, right? The surface area of the outside surface area of the sphere, 4 pi r squared. And if you actually use equation from equation 1, this equation, you would get, can anybody tell me? QR. Fancy R dot, right? What was that? Fancy R dot over 3. But you need to calculate that R is equal to capital R times capital R times 4 pi r squared. And we find what? Fancy R dot times 4 over 3 pi r cube. What is this 4 over 3 pi r cube?
Volume.
Volume of the sphere. Excellent. So again, we found that whatever it loses is being generated inside this shell. It makes sense. It makes total sense. So you can also yeah, it also gives us an idea about what is the volume of the sphere, right? If you don't know the volume of the sphere, you can calculate using this this trick. But if you know the volume of the sphere, it makes total sense that the whatever it loses is being generated inside, because it's at a steady state. Otherwise, the temperature of the sphere would change with time. Okay, that's it.